In this example, we want to test the hypothesis that the average height of Bunker Hill students is 68.6 inches. What we did is we took a sample of 25 students from the school, and that sample gave us an average height of 69.1 inches. So the question asks us is, does that sample indicate that the population mean height, the mean height of everybody at the college, is actually greater than 68.6 inches? Now you might first think that taking this sample of 25 students, there is only a half an inch difference. But that's what we're going to use a hypothesis test to check. We're going to check the statistical significance of that half an inch difference. Every hypothesis test starts with a null hypothesis. That's the statement that you're assuming is true and the statement you're putting to test. We do hypothesis testing on population means. So we're testing that the population mean is 68.6 inches. The question asks us to test whether that population mean height is actually now greater than 68.6 inches. So in addition to our null hypothesis, H0, we put forth an alternate hypothesis, H1, which is going to be that the mean is greater than 68.6 inches. This type of test is called a right-tailed test because we're going to compute a probability down on the right tail of a distribution. And we're going to use a 5% level of significance, which is our value for alpha. The level of significance, again, is the probability with which we are okay in being wrong and rejecting the null hypothesis. In other words, at the end of the test, if there's less than a 5% chance I'm wrong, I'm going to reject my initial claim that the average height is 68.6 inches. To do this test, we're basically going to do something similar to our original example, in that we're going to find the probability that if the average height of Bunker Hill students was actually 68.6 inches, what is the probability I could have gotten a sample of 25 students and had those 25 students average out to 69.1 inches or more. To compute that probability, we have to decide between using a standard normal distribution or a student's t-distribution. The basic difference is that, do I need to compute a z-value or do I need to compute a t-value? Z-values rely on the fact that I know the population standard deviation, sigma. So if I know sigma, I can compute a z-value, which means I can use the standard normal curve. In addition to that, though, if I want to use the standard normal distribution, I have to make sure that this sampling distribution is also normal. And the requirements for that are that either the original population is normally distributed, which I'm referring to as x, or I take a sample size of at least 30. In this particular problem, I don't have a sample size of at least 30, but I'm going to go under the assumption that the population has a normal distribution. So I can use the standard normal distribution as my sampling distribution, which means I can compute a z-value. So I took my sample mean of 69.1 inches and I computed the z-value for that, and I calculated it to be 2.78. What I'm going to do with that is find something called a p-value. The p-value is essentially the probability that my z-value, or my sample mean, is greater than the values that I calculated. I want to know what's the probability I could have got a sample mean of at least 69.1 inches or higher. That's the same as the probability that z is greater than or equal to 2.78. I can get that p-value off of the normal table using my regular procedures. I would have to look up 2.78 on my normal table. That would be the area to the left when I found that. If I take a look at my normal table and I go to z is 2.78, I see I have a probability of 0.9973. That's the area to the left of z is 2.78. So I subtract that from 1 to get my p-value of 0.0027. P-values are the same probabilities we've been calculating for Chapter 6 and 7. They just have a special name when we do hypothesis testing. So basically what I've concluded here is that if the average height of the college was actually 68.6 inches, the probability I could have got a sample mean of 69.1 inches or higher is only 0.0027 or 0.27%. Extremely small. So if I were to reject my original claim, right, the probability I would be wrong is only 0.0027. Because that probability is less than my level of significance, I was okay with up to a 5% chance of being wrong. According to my test, I only have a 0.27% chance of being wrong. So I'm going to go ahead and reject my initial claim. I'm rejecting the claim that the average height of Bunker Hill students is 68.6 inches. And by default, I'm now going to adopt the claim that the average height of Bunker Hill students is greater than 68.6 inches.